Hi everyone. In this video, I am going to talk to you about the topic of spectrophotometry, which is a technique for analyzing concentration of an unknown solution. And because we are dealing with visible light spectrophotometry, which is a spectrum from roughly 400 nanometer to 700 nanometer. So this is the range we are dealing with. Let me just show you this is the visible range. And it's important for you to remember the color wheel. Your color wheel, if you look at the order of the colors, will help you understand the complementary color relationships. So we have a red color, orange. This is in the order of the spectrum from lowest energy to highest energy. Lowest energy color is red. The next color is orange. The next one is yellow. The next one is green, then blue and purple or violet. So if you build a color wheel, it doesn't matter where you start. Just start with a circle, divide it into 6 slices like a pizza with equal size slices. So it would be like saying you are essentially like doing this. And then start in any direction. I just happen to start from the top. And you can go in any direction and put in your colors. And the acronyms ROY, G, BEV are easy to remember. Remember to do your ROY, G, BEV on the color wheel. So the color wheel gives us the complementary color relationship, and I'll explain that. So with this spectrophotometry method, we need to work with a colored solution. And what we do is we place the colored solution inside of a sample holder that's called cuvette. And this cuvette is sort of like a test tube, but it has optical clarity so that it does not interfere with the light. The test tube, it looks like glass that's very clear, but it's often plastic. And sort of like your prescription glasses that are mostly plastic and they're very clear. It has that type of optical quality to it. And the instrument it can be quite complicated, but I'm just showing you the very basic components. The instrument comes with a light source. Think of this as a white light source. As you recall, white light is addition of all these rainbow of colors. And the white light has the spectrum, a full spectrum from red to violet. Then there is a wavelength selector switch somewhere on this equipment. And there are different versions of this equipment, but I'm just talking about the more basic ones. And the wavelength selector could be a prism, but more commonly it's a diffraction grating, which is sort of like the CD. They're looking at the surface of a CD, a compact disc, and seeing how light breaks up into their components. So the breaking of the light doesn't really happen before. The white light is just combination, but I was just showing you that it's addition of all these colors, ROY, G, BEV. Then the wavelength selector picks a particular wavelength and passes it through the solution. This wavelength is going to be an absorption wavelength. So we call it lambda. Lambda is the Greek letter that's used for wavelength, and we call it lambda max. Lambda max is maximum absorption wavelength. And it has to do with the particular solute that we deal with. So we don't have any kind of visible absorption that would be detectable for the solvent being water, but it is the solute that's often colored that we work with this technique for. And so once we determine what is the maximum wavelength of absorption of light, the wavelength selector passes that wavelength. And usually it doesn't, I'm showing you that we are passing like 3 colors, but we may, when we pick a particular wavelength, we may only pick one color. In this case, I can see that, if the solution absorbs in the range of orange, yellow, and green, but I may just select the green. Let's just go with that as the wavelength that's being absorbed. So let's look at our complementary color. So if you absorb on the green zone in the color wheel, look at your color wheel. If you absorb a wavelength equivalent to the green, it means that you are passing the red across. So the complementary relationship are opposing colors. One color is transmitted, one color is absorbed. If you absorb green, the solution is going to look red to you. And this is the reason why oceans are green, because the daylight that goes through the ocean water, the components that are absorbed on the daylight is typically the reddish, the reddish component of the white light, and then the oceans appear as green. Oceans are often blue-green because ocean water absorbs red-orange, and that's the complementary. The complementary to red-orange is blue-green. So blue-green is what you see when red-orange is what the solution absorbs. Okay, so now I've just put an eye here. This is what I see. For example, if you pass your white light through your solution, the solution being this cuvette sample holder, and now I can see that orange, yellow, and green are absorbed. They don't get passed. The solution filters it out. But then a combination of red and blue is being absorbed, being transmitted. Red and blue, when transmitted, gives you this purple color. So a solution that looks purple to me is because it's passing red and blue. So now remember, I have to work with absorption because I want to know what portion of light, what intensity of light is being absorbed, mainly because the concentration of solute is related to the amount or the intensity of absorption of light at that particular wavelength. I'm going to say it another way. In other words, if you have more solute in the solution, you're simply going to absorb more of the intensity of the green that's going through the solution. And then there's going to be an indication of what the absorbance is. So I'll explain a little bit more about that. So for example, if you have a situation where you're dealing with, right here, a cuvette, and in this case, I'm going with the green being what's being absorbed. So we are picking a wavelength of roughly 550 nanometers, as I have over here, because I know this is the wavelength of good absorption from the solution, and the solute absorbs that. So we are passing a light intensity of 550 nanometer with certain intensity through the solution, and because the intensity that leaves the solution is related to the concentration of the solutes within this solution, okay? In other words, more concentrated solute, the intensity drops because these solutes are absorbing the light. So I output will be less. So I output will be less than the initial I or intensity that goes through the solution. And this establishes an important parameter that's called transmittance. So percent transmittance is the ratio of the output intensity over initial intensity times 100. But the transmittance itself is not a linear function of concentration. I want to find a better variable, and that better variable is the log of the fraction of transmittance, not the percent, but the fraction. So if you take negative log of I out over I in, or I, you develop this variable called absorbance. So for us, absorbance is the most important variable. Of course, transmittance is something you should know as well in terms of definition of these intensities. And this is the fraction. If you multiply by 100, you get percent. So you can convert from absorbance to transmittance using this equation, the second equation that I just showed you, which is negative log of output intensity over initial intensity, which is what we call the fraction of transmittance. This right here is transmittance, but in terms of its decimal value, not the percent. If you want to work with the percent, then you can use this equation to go. Put in the percent value for transmittance and do 2 minus log of that, and you get absorbance. Might be a little simpler equation for you to work with, but they give you the same results. So this analysis was developed, but it's called Beer's law analysis when absorbance becomes linearly proportional to concentration of the solute that's colored. And if you get it into a simple equation, which is again linear, this equation has format y equals m times x, you get what we call Beer's law. So this is Beer's law equation. And the Kb is called Beer's law or Beer's constant. So the Kb, of course, is the slope of absorbance versus concentration plot. So if you do a linear plot of absorbance versus concentration, and you should get several points that fall into the line, and typically this graph goes through 0, 0, because if there is no absorbance, there is no concentration. Concentration is 0 when absorbance is 0. Therefore, the slope of the graph is equal to m. And typically Excel is perfect for analyzing for these graphs and getting the slope, because we want to be able to predict the concentration of an unknown solution. The whole point of doing this is to use the spectrophotometry and this equipment to determine the unknown concentration of a solution. So in order for me to do that, remember I have to have several points here. I have to have different points. Usually what defines a straight line is really just 2 points. So you could use 0, 0 as 1 point, and then one of the other points, that would be your known solution. But we do several points because we want to be able to trust the data. With 1 point, you could make a mistake and you're not really sure if your slope is correct. But if you do several determinations for absorbance and concentration of known solutions, you can have a lot more trust in your lab data. So this gets into working with preparation of standard solutions. The standard solutions are solutions of known concentrations. It is the same solute that I'm dealing with an unknown solution of. Let's say someone gives me an unknown solution and ask me, what is the molarity of this solution? Well, first I have to prepare a series of known concentrations of the same solute, run it through this equipment, which is called a spectrophotometer, get the absorbance, or you can get percent transmittance and convert to absorbance, as I showed you with this equation. And then you can do your plot. This is called Beer's law plot. Once I have my Beer's law plot, I use Excel to get the slope of the plot. And now you have your Beer's law equation. Once you know the Kb, Beer's law constant, you have an equation that you can apply to any unknown solution, whether the concentration is within this range or outside the range. But typically we stop on the outside zone because I don't want my unknown solution to exceed the most concentrated solution of the standard. And if that's the case, I would be doing a dilution to lower the concentration and back calculate the original unknown concentration. More on that later. So here I have prepared from a stock solution. I prepared 4 solutions that these solutions are my standard solution. So imagine that you have some amount of the stock solution, and because the stock solution, and here I'm showing you this green color, okay, and I started by saying green color here, but this is the color that's being absorbed, and the color that you see here is not going to be green. And so notice that if your color that's being absorbed is green from your color wheel, the color that's being transmitted or you see is red. So my solution here is going to be a red colored solution. So let's just go ahead and, and pretend that these are red colored solutions, but we'll just work with green as just some other color, okay? So anyway, my initial concentration, this is my stock solution, is going to be way more concentrated. So I'm going to just show it as like a darker green because it's more concentrated in whatever solute you have, okay? So then I prepare these lower concentration solutions from it. So here to do this work, I take certain volume of the stock solution, I put it in solution 1, and it might be like this much, and then you add water to it to bring up the volume. And then for solution 2, you add a little bit more, and you still add your water to it to dilute it. For solution 3, you add a little bit more, and you add your water to dilute, and for solution 4, even more, and add your water. So you can see that all of these solutions 1 through 4 are dilutions from my stock solution. And so how much do I take from the stock solution? It has to do with molarity 1. I hope you watched the video on concentrations. So it has a certain molarity, and you're gonna need to calculate the V1, I'm sorry, not M1. You need to calculate that because you have to decide on the concentrations of these solutions. That's called M2, or the final concentration for solutions 1 through 4. And you also have to decide how much volume of these solutions you want. So let's say if somehow your test tube, all you need is a capacity of 10 milliliter. Therefore, you may want to do like 1 ml, 2 ml, 3 ml, 4 ml for each stock solution of solutions 1 through 4, and add the balance quantity as water. With 1 ml, I add 9 ml of water, that'll be 10 ml total. With 2 ml of the stock solution here for solution 2, you add 8 milliliters of water, and therefore you come up to 10 ml. With 3 milliliters, you add 7 milliliters of water. With 4 ml, you add 6 milliliters of water. So you are getting essentially a more concentrated solution with the case that you add the least amount of water, which is solution 4. So with these solutions, now I would run the spectrophotometry. So obtain absorbance A for each standard solution. And as I said, you could also get your percent transmittance and convert to absorbance mathematically. That's also done sometimes. Sometimes we get slightly better results, more precise results if you do it that way, and it's preferred. And once I have the absorbance, and remember you did your M1V1 equals M2V2, the dilution for all of these solutions, and you know the concentration of these solutions now. I'm going to run through an example so it'll be more clear for you too. So once you have that, then you can do your plot, the standard Beer's law plot. You can prepare it. So let's just say that my stock solution, the dark green material, is, let's say, 3.5 molarity of some solute. Okay, not going to specify the solute. And I want to go through a process of dilution here. And let's say that I take, actually I'm going to lower this because this may be in reality like too high. So let's go 0.35 molarity of the solute. And my V2, because in every case I'm dealing with 10 milliliters, so my V2 is 10 milliliters. And let's say I want to stick with 3 sig fig, so I put 0.35. And my V1 is a question mark. I don't know how much of the stock solution to take. And my M2 is going to be a question mark. And my, what's the one left over? So V1, M1 will be 0.350 molarity. Now, I've already decided that I want a series of, say, 1 through 4 ml, as I showed you up here. Solution 1 has 1 ml of the stock. Solution 2 has 2 ml. Solution 3 has 3 ml. Solution 4 has 4 ml. So essentially, I know my V1 in each case. Let's say you're doing with case 1, your V1 would be 1 ml, and this would be your solution 1. So how do I get the final concentration or the standard solution 1's concentration? You just get M2 is equal to M1 times V1 divided by V2. This is where that dilution factor becomes a little important with these cases. This is from the equation M1V1 equals M2V2. So my M1 is 0.350 molarity. My V1 is 1 ml. My V2 is 10 ml. So you're doing a 1 to 10 dilution factor to the 0.350. So 1/10 of 0.350 is a value of 0.0350 molarity. You need to move the decimal. Divided by 10 means move the decimal one place to the left. So I found my solution 1's concentration. And solution 2's concentration is done the same way. Now your V1 is 2 ml. So your M2 is equal to 0.350 molarity times 2 milliliter of stock solution diluted to 10 ml. So 2/10 of 0.350 is going to be 0.0700 molarity. We are following good significant figure rules so that everything would be 3 sig fig. And for solution 3, please use M1V1, M2V2 and confirm this for yourself. It would be 0.350 molarity times 3 ml divided by 10 ml. So 3 divided by 10 times 0.35 is 0.105 molarity. See, it's getting more concentrated. I started with the least concentrated solution 1, solution 2 more concentrated, and this by a factor of 2, solution 3 by a factor of 3. And the last solution is solution 4. This is solution 3. And then the last solution 4 would be M4 is 0.350 molarity times 4 ml divided by 10 ml. So 4 divided by 10 times 0.35 is 0.140 molarity. So solutions are getting just more concentrated in every case. So you can see that compared to with the first solution, the fourth solution is more concentrated by a factor of 4. So now I have these predictable dilutions that I performed on my stock solution of 0.350 molarity that I started with. So this is your dark solution to the right. And then you prepare these successive dilutions of solutions 1 through 4. And in every case, I just figured out what my concentrations are by doing these calculations. Concentrations C1 through C4. Now you need to take your solutions and put it in your cuvette, stick it into this spectrophotometer, and get the absorbance values for it, or percent transmittance, and convert to absorbance. So now you have a set of concentrations and absorbances for your solutions. Now you're ready to do your Beer's law plot. So I'm going to create a Beer's law plot for you, and let's just put a list here of concentration and solution. So, well, let me just do it as solution and concentration. And then you can do, let's just stick with absorbance A. So solution 1, 2, 3, and 4. The concentrations are 0.0350 molarity, 0.0700, 0.105, and 0.140. You can just put in these numbers onto Excel and use the spectrophotometer to calculate absorbance. Or if you have the percent transmittance, you can just do percent T over here, and then you can create a formula cell. Remember, if you have the percent value, not the decimal, the formula that you're going to put on here would be absorbance is equal to 2 minus log of percent T. So if you just put in this formula and you start with an equal sign for your formulas in Excel, you can essentially have Excel calculate it for you. So whether you get those absorbances or get percent T's and then have Excel calculated for you, I'm just going to make up some numbers so we can get this work done. Let's say solution 1 has an absorbance value. It gives you an absorbance value of maybe 0.015. And let's just stick to 3 sig fig. And, the solution 2 will be 0.0302. Solution 3 would be 0.0455. And the last one would be 0.0609. So here we have 4 absorbances that would be calculated from percent T, or you could be getting this directly from the instrument, but I think the preferred method is percent T conversion to absorbance. And once you calculate them on Excel, you now have your concentrations and absorbances. Concentration, absorbance. And this should be a nearly linear graph. I made it deliberately slightly less linear because we're going to use Excel to get us the slope of that. So I'm going to pause this video, go to Excel and do the work. I want you to do the same thing and make sure that you set your intercept equal to 0, because we just want the equation as y equals mx. Remember, y is your absorbance and x is your concentration or molarity. Molarity concentration, and this is my absorbance. And this is going to be, so I want you to prepare a Beer's law plot. And with this plot, make sure that you list equation on the graph, and please follow all good graphing techniques. Make your graph full page and call it Beer's law plot, and you also list the r-squared value, which is the correlation coefficient. Remember, the closer the r-squared to 1, the better linearity you have. The trend line, the linear trend line follows your points better. And so there's more confidence on your linear graph. And having the equation on the line of the line, you can now calculate any unknown concentration based on its absorbance. Okay. So this is your assignment to do this work on Excel. And I want you to calculate several things about this. So I want you to calculate. This is using the Beer's law equation. Once you have your graph and equation of the line, you have your really Beer's law equation. Calculate these situations here. So situation 1 would be the unknown concentration of a solution which gives an absorbance value of, so if we imagine I've given you an unknown solution that has an absorbance value of 0.0505. So your A value is equal to 0.0505. Absorbance does not have any units. We just call it absorbance. And the concentration is going to be in molarity. So this is not something you want to plot on that graph. You're done with the plot. By preparing a Beer's law, you already did it. The Beer's law plot is for the 4 solutions that I gave you their absorbance and concentrations. So this is an application of what you just did. Someone hands you an unknown solution of the same solute. You don't know the concentration, but you run it through the cuvette and you measure an absorbance of 0.0505. What is the concentration of that solution? That's what you're trying to calculate. So this would be the first problem that you have here, is that. And then the second problem would be calculate unknown concentration of a solution which gives an absorbance value of 0.0250. So I'm essentially giving you like 2 assignments on this data here. So please report. So let's call it for unknown. Let's call this one unknown A, and this is unknown B. So I want you to write on your graph. This is just that one page that you're going to turn into me. On your graph, write down what the concentration of A is and concentration of B is. Both of these will be the molarity. You can just handwrite it anywhere on that graph that there's space, and give me the concentrations for this part 1 and part 2. Okay? So go ahead and work on that, please.